ActionNET Gateway provides a solution that ensures interoperability between different IEDs. It converts different client protocols to a server protocol. In the example presented, we will convert Modbus, DNP 3.0 and IEC-60870 client protocols for the IEC-104 server protocol. The basic structure of the ActionNET Gateway is presented in this scheme. The IEDs or systems send information through their native server protocols. These information are received by the ActionNET Gateway through the respective client protocols and, automatically, converted to the defined server protocol, without the need of any additional configuration. Then, the information is forwarded through the server protocol to the system that is requesting it. The ActionNET has dozens client and server protocols, which are used in automation systems. In this table, the main ones, applied to the electrical area, are highlighted. To speed up the configuration of a gateway application, a set of components was created, representing the main relays, meters, and other elements used in substation monitoring. These components include the best practices for configuring these IEDs, in terms of addressing communication points, alarm rules, display, and forwarding data to history. The configuration of a gateway application must follow the following structure. First, the data acquisition step is customized, and after the data distribution or transmission data is customized. For a better understanding of a gateway application, we will develop an example project, according to the configuration presented. In this example, we have two feeders bays, a transformer bay, and a line bay. The communication protocols, used to exchange data with the relays, will be IEC-60870 and DNP 3.0. To serve the data to the top-level application, the IEC-104 server protocol will be used. As previously mentioned, we will start customizing the communication with the IEDs. Create a new project with the specified number of tags. With the created project already open, go to Run, Extensions, Components, and import the listed components. To import a component, simply select it, and then click on the Specify button. In the opened window, just select to add a new component. In the end, the project will be as presented. Then we must make the settings, as specified in this table. The next step is to configure the channels and nodes to communicate with the four IEDs. It should be noted that the name of the channels and nodes must be the junction of the parameter inserted in the comment and category columns, according to the scheme. To configure the channels and nodes, go to Edit, Devices, and perform the settings, as shown in the Channels and Nodes tabs. This will be the appearance of the project at the end of this stage, leaving only the configuration of the relays using the IEC-60870 protocol. Select the object to be configured. Click on the right mouse button. Select Go to Template. In the comment column, enter the logical nodes shown at IEC-60870 address. Then the deploy extension must be executed. This extension automatically generates all communication points with the associated events, history and addresses. Go to Run, Extensions, and in the Import tab, double-click the deploy icon. Check all the options presented, and click the Create button. Wait for it to run. In the end, the number of items created will be displayed. The data acquisition stage is completed. We will now proceed to the data submission stage. Any server protocol can be used. In this example, we will use the IEC-104 protocol. The generation of IEC-104 server point address is defined within the application. In this example, a number was considered for each SD used, see Table 1, and a second number for each ID associated with a bay, Table 2. The information object address has the following structure, and its generation is done by concatenating the string that designates the ASDU, the number of that ASDU defined in Table 1, and the number of the ID, defined in Table 2. The address of the points is configured in their column comments, in the templates that describe their IEDs, shown here. Finally, the configuration will be as follows. The next step is to create the channel and node for the IEC-104, as shown by the two arrows. Then, let's do the settings for deploy the points of this server channel. Remove the configuration of the level and category columns of the four configured bays. Then, perform the individual configuration of each bay, selecting it, after clicking the right mouse button and go to Template option. In each template, configure, in comments, the address of each point, as explained previously. In the case of the feeder bays, we must execute the customization of each one separately, executing the deploy for the first, and after for the second. The Object tab, for the first and second feeders, will be as shown. The step of configuring the gateway is completed. To finish configuring the ActionNET gateway, go to Info, look for the Settings tab, and set the family property to OPC Server. This finalizes the configuration of the gateway, removing several features like the man-machine interface, and others. As presented, the purpose of a gateway is to read data from several IEDs, with different protocols, and serve in a single protocol, an external application, such as a SCADA in the cloud. We will then build this application, using a new component, as stated at the beginning of this movie. As in the previous project, we must perform the same steps, that is, create a new project, import the component, create the channel and the communication node, perform the base configuration step, as shown. Then run the extension deploy. The structure is similar to the previous project, just follow the following steps. The setup is complete. Now, just select the bays created, copy, and paste them on a specific project screen. All elements will be loaded, just order them, according to the single-line diagram. The application is complete. We can confirm its effectiveness by running a device simulator. In this example, we will use a simulator IEC-60870, simulating the feeder bay. The feeder simulator, the gateway, and the cloud server will run together. Based on this component methodology, adding new features to the project is simple, just add a new component that includes this feature. For example, if in this architecture we want to add a meter attached to the transformer, to manage the asset, in our component bank, just select the corresponding meter, whose function must be integrated, into the gateway. After importing the meter component, and making its settings, the gateway will send its data, to the application in the cloud. As in our example, the objective is asset management. We add the appropriate component, from the library, including the functionality transformer monitoring to the cloud application, allowing the management of this asset, through the presented screen.